Welcome back. I am so glad you're joining us for today's deep dive. We are taking a journey today that is going to completely reframe how you conceptualize the physical world around you.
Yeah, it really will.
Because the ground beneath your feet is not just a static mass of rock. It is a highly categorized, aggressively explored, and surprisingly dynamic frontier. Okay, let's unpack this. We are looking at the intricate and heavily regulated world of new mineral discovery.
Right, and it's a world most people don't even know exists.
Exactly. And we've got a formidable stack of sources today. We are anchoring this entire discussion on a brand new, freshly approved mineral species. We have its official mineralogical database page from MinDat. We also have its Catalan Wikipedia entry.
Which, as an aside, is just a brilliant indicator of how instantaneously these geological data points disseminate globally.
Yeah, the internet is amazing for that. We are also bringing in a late 2025 mining industry news bulletin from MiningCom to ground this in macroeconomics. And to cap it all off, we have the colossal January 2026 master list for the International Mineralogical Association.
It is a massive stack of data. And what's fascinating here is that it shatters a very common misconception. I think most people operate under the assumption that the map of the Earth's chemistry was finalized centuries ago.
Right, like we found all the rocks already.
Exactly. We tend to view mineralogy through this historical lens, assuming the inventory of the solid universe was completed around the same time the foundational elements of the periodic table were being locked in. But as this data proves, geology is a rapidly evolving, highly competitive science. We are still mapping the lithosphere, quite literally, atom by atom.
And our mission today is to pull back the curtain on that exact process. We are going to explore the rigorous gauntlet that a newly discovered lattice of elements has to run to go from a subterranean anomaly to an officially recognized scientific fact.
It's quite the journey.
It really is. And we're going to look at the macroeconomic realities driving these discoveries, specifically how finding a microscopic, seemingly obscure sulfide mineral acts as a geopolitical asset in the global supply chain for modern technology. And then we're going to zoom way out. We're going to analyze the sheer staggering scale of the 1,600 known minerals that make up our planet, and crucially, the bodies beyond our planet as well.
It functions as a taxonomic detective story, a masterclass in deep earth chemistry, and a leading indicator for the future of the global energy transition, all synthesized into one discussion.
So let's dive right into the anatomy of this brand new mineral. The star of our show today is Jinxuiite.
Spelled Jinxiuite.
Right, pronounced Jinxuiite. In Chinese, it's known as Jinxian. This mineral was officially recognized by the international community in November 2025 and given the official international code IMA 2025-059.
And when you analyze the crystallographic data from that MinDat database, it becomes immediately apparent that Jinxuiite is not a simple terrestrial formation. It is a highly complex sulfide. The empirical formula is Ni18b/2sb(a)16.
That stoichiometry there is just incredibly dense. We are looking at an 18 to 2 to 1 to 1 to 16 atomic ratio. Let's look at the elemental breakdown by weight because it reveals a highly specific, very volatile formation environment.
Yeah, the recipe is wild.
It's like a highly specific recipe. You have a nickel base making up 48.37% of its weight. Sulfur constitutes 23.49%. But then you introduce these heavy metalloids into the matrix. You have bismuth at 19.14%, antimony at 5.58%, and arsenic at 3.43%.
Which is strange, right? Because typically, introducing heavy toxic metalloids like bismuth and antimony into a nickel-sulfur bond would disrupt the lattice entirely. But here, they stabilize in a highly specific configuration.
And that structural stabilization is exactly what sets it apart as a unique species. The MinDat source gives us the crystallography data, placing Jinxuiite in the tetragonal crystal system. Specifically, it belongs to class 4 metal-meter, also known as the ditragonal dipyramidal class, with a space group of I4 metallite.
Let me break down what those numbers and systems actually mean for a second.
Please do.
When we talk about a tetragonal system with an I4 meterium space group, we're looking at a highly symmetrical, body-centered lattice. It's akin to the lattice structures we often see in material science, particularly when looking at the lattice strain in certain piezoelectric materials or high-temperature cuprate superconductors. The atoms are arranging themselves in this stretched cube configuration where that specific ratio of nickel, bismuth, antimony, arsenic, and sulfur repeats with absolute mathematical perfection.
It's mind-blowing that nature just builds that in the dark.
It is absolute structural precision. The database provides the exact cell parameters, the fundamental dimensions of this microscopic architecture. The A-axis is 10.2292 angstroms, and the C-axis is 10.8101 angstroms.
That yields a width-to-height ratio of 1 to 1.057, so it's just marginally taller than it is wide.
Exactly, resulting in a unit cell volume of 1,131.13 cubic angstroms.
And because of that exact atomic architecture, the Strunz-Minnick classification system slots it in at 2BB10. The 2 designates it as a sulfide or sulfosalt. The BB indicates a metal sulfide, where the metal-to-sulfur ratio is greater than 1.1, specifically containing nickel. But what I find incredibly compelling in the data is its structural relationship to another complex mineral, arsenohauschkornite.
Arsenohauschkornite, which has the formula 918 by 3s16.
Right. So look at that substitution.
The substitution is fascinating. In Jinxuiite, the geological environment essentially forced one atom of antimony to swap out for an atom of bismuth within that arsenohauschkornite framework.
Just one atom.
Just one. That single elemental substitution under deep earth pressure and temperature creates an entirely distinct mineral species.
It is a testament to how slight variations in a hydrothermal fluid can yield entirely different solid-state chemistry. But let's bring this out of the theoretical crystallographic realm and locate it geographically. Because the type locality, the exact geographical coordinates where the holotype was extracted, is meticulously documented in both the Mindat and Catalan Wikipedia entries.
It makes it very tangible.
It really does. It was extracted from the adit of ore body number 3 in the Longhua Nico deposit. This is in Jingzhou County, Levin, within the Jinxuiite Autonomous Region of Guangxi, China.
And the specific geology of that region is critical to understand here. Guangxi is known for its complex tectonic history and intense hydrothermal activity. That creates the exact kind of subterranean high-pressure, high-temperature chemical soup required to precipitate a mineral as complex as Jinxuiite.
And it wasn't just lying on the ground. The documentation specifies it was found in an adit.
Right, a horizontal passage driven deep into the mine shaft.
We are talking about researchers from the Chinese Academy of Geological Sciences operating deep underground, analyzing the rock face in a nickel-cobalt mine, and identifying a microscopic inclusion that just didn't align with known metallurgical profiles. But extracting the sample is only the first step. The burden of proofs required to introduce a new mineral to the global scientific record is remarkably high.
Oh, it's an incredibly rigorous gauntlet. You can't just claim you found a new rock. This brings us to the keepers of the keys, the IMA approval process.
So the discovery team, Heijin Tang, Qinshin Liu, Jiangyan, and Zhending.
Right. They couldn't simply publish a paper asserting a new discovery. They had to submit an exhaustive dossier of empirical evidence to the IMA CNMNC.
The International Mineralogical Association's Commission on New Minerals, Nomenclature, and Classification.
Exactly. The CNMNC has been the global arbiter of mineral taxonomy since 1958. To secure that November 2025 approval vote, the researchers had to prove beyond any reasonable doubt that this specific structural and chemical configuration had never been documented in human history.
And the primary mechanism for that proof, as highlighted in the source data, is X-ray powder diffraction.
Yes. X-ray powder diffraction is the gold standard for this type of analysis. By bombarding the powdered sample with X-rays and measuring the angles and intensities of the diffracted beams, researchers generate a unique structural fingerprint based on Bragg's law.
And the Mindat file lists the specific intensity spikes at exact D spacings for Jinxuiite, noting a massive 100 intensity spike at 2.775 angstroms.
You cannot fake that data. It is a direct mathematical reflection of the internal atomic planes.
And then there's the holotype requirement, which is just fascinating. It essentially establishes a physical chain of custody for the solid universe. The source notes that catalog number GMCTM 20025020 is secured at the Geological Museum of China in Beijing, while sample JX1 is held at the State Key Laboratory of Deep Earth and Mineral Exploration.
They have to be locked away for posterity.
But taking that a step further, the reliance on these physical holotypes presents a fascinating reality about the evolution of science. We mandate the preservation of the physical rock because analytical techniques are constantly evolving.
This raises an important question about the longevity of data. Why keep them? Well, 50 years ago, mineralogists relied on wet chemistry and early optical crystallography. Today, we use electron microprobes and synchrotron X-ray diffraction. A century from now, the technology will be completely unrecognizable.
So we keep the holotypes locked away because future generations with better technology will inevitably need to retest these original gold standard samples to recalibrate taxonomic boundaries.
Exactly. It's an incredible act of preserving scientific heritage, ensuring that empirical ground truth always remains accessible.
And once that burden of proof is met, the mineral receives its official designation. The IMA assigned Jinxuiite the symbol JX, adhering to the 2021 WAR guidelines for mineral abbreviations. It's like a newly discovered element getting its spot on the periodic table, but for minerals. It systematizes the literature, allowing geologists to map massive datasets with standardized shorthand.
But the taxonomy and the rigorous verification process ultimately serve a much larger, highly pragmatic purpose. The discovery of Jinxuiite is not merely an academic triumph, it is a critical macroeconomic indicator.
Right. Why go through all this trouble? Does this discovery actually matter outside of a museum?
Yeah,
Here's where it gets really interesting. We aren't just looking at rocks, we're looking at a geopolitical vector.
absolutely.
The Mining.com bulletin from late 2025 explicitly points out that Jinxuiite was found in a hydrothermal nickel-cobalt deposit. And if you follow the electric vehicle and grid storage supply chains, you know that the global industry is currently locked in a fierce competition for high-grade nickel and cobalt.
They are the absolute backbone of modern technology.
These are the fundamental constraints on the energy transition.
Yes, and the discovery of Jinxuiite is a key to unlocking specific types of highly desirable ore bodies.
Yeah.
The industry is currently trying to manage the environmental and economic costs of mining laterite nickel deposits, which are close to the surface but require massive, highly carbon-intensive, high-pressure acid leaching to process.
It's messy.
Very. The alternative is high-grade hydrothermal sulfide deposits. These are much deeper, much harder to find, but they yield the Class 1 nickel required for high-performance batteries far more efficiently.
Which is exactly why the Mining.com bulletin emphasizes that the discovery of Jinxuiite alongside Geopolitics, the Nibis mineral previously found by the same academy in the same region, provides valuable guidance for future ore exploration breakthroughs.
Right, because they aren't trying to mine Jinxuiite to put it in a battery.
No, it's laced with arsenic and it occurs in microscopic quantities anyway. Jinxuiite is an indicator species.
That is the core of orogenesis analysis. By understanding the paragenesis of Jinxuiite, by reverse engineering the exact formation fluid conditions, the temperature, the pH, the fugacity of sulfur required to precipitate the specific structural lattice, geologists can map the geological history of the region.
It acts as a highly specific diagnostic tool. If a mining company or a geological survey team detects the chemical and structural signature of a complex sulfide like Jinxuiite in a core sample, it acts as a microscopic X marks the spot.
Exactly.
It tells them that the surrounding deep vein architecture likely harbors a massive, lucrative, undiscovered hydrothermal vein of nickel and cobalt. Mineral taxonomy in this context is a critical intelligence asset for resource extraction.
If we connect this to the bigger picture, you start to realize that every single new mineral discovery adds a critical data point to our understanding of the Earth's thermochemical engine. Jinxuiite is just one newly rendered pixel in a massive global puzzle meticulously maintained by the international scientific community.
Which brings us to the most expansive source in our stack today, the January 2026 update of the IMA list of minerals. This document is a staggering achievement. We are looking at the master inventory of the solid universe.
The document formally presents the selected information on the 6,200 currently valid mineral species distributed via the IMA CNMNC.
6,200 unique, naturally occurring, solid-state chemical configurations. And the list is incredibly dense with metadata. It provides the empirical formula, the year of approval, the country of origin, and a very specific IMA status code.
Yeah, let's break those down. The A code stands for approved. That's applied to minerals discovered and rigorously vetted post-1958, like Jinxuiite.
The pre-1958 context is where it gets highly complex. The G code stands for grandfathered. These are minerals discovered before the IMA was established in 1958, which are generally considered valid species. But as we discussed regarding the holotypes, the G classification presents a unique vulnerability in the taxonomic framework, because early mineralogists didn't have X-ray diffraction. When aragonite calcium carbonate was described in Spain in 1791, or when elemental arsenic was formally documented from Germany and Norway in 1755, they were relying on physical properties like cleavage, streak color, and specific gravity.
We've been doing this for almost 300 years and we're still finding new ones.
The fact that we have grandfathered minerals that hold up to modern spectroscopic analysis is impressive, but it also explains the necessity of the RDNE and Q codes on that list.
Precisely. R denotes a redefined mineral. This indicates an older species whose chemical definition or structural parameters had to be tweaked or corrected using modern analytical technology during the IMA era.
And the Q code stands for questionable.
Right. These are poorly characterized minerals from the past whose validity is highly doubtful under modern scrutiny, yet they remain on the list for historical tracking and literature continuity.
Revoking a mineral status is almost as rigorous a process as approving one. The burden of proof to definitively state that a historical mineral is merely a variant or an impure mixture of other known minerals requires an immense amount of peer-reviewed data. The maintenance of this 6,200-member list is a Herculean, deeply collaborative global effort.
You see that in the acknowledgments section.
Oh, the acknowledgement section alone is a massive directory of the leading minds in geochemistry and crystallography, from Malcolm Back to Lunita Zaharia. It shows this is a passionate, global, collaborative effort.
It also serves as the definitive style guide for the discipline, explicitly establishing that mineral names are common nouns.
Which is why they only receive capitalization at the beginning of a sentence, or within the structured confines of an index or table. It standardizes the global lexicon.
It acts as a snapshot of human history and science.
The contrast within this list is breathtaking. You have Jinxuiite, an A mineral minted in 2025, sitting in the same database as minerals documented during the Renaissance. We have been systematically categorizing these distinct chemical matrices for 3 centuries, and the rate of discovery is actually accelerating due to better technology.
It's accelerating rapidly.
Reading through this master list is completely absorbing. You spot geopolitical trends, historical biases, and then you hit these profound paradigm-shifting anomalies. I want us to take a highly focused, rapid-fire analytical tour through just the A and B sections of this massive database, because the implications of some of these entries are extraordinary.
I agree. The database is full of outliers that challenge our fundamental definitions of geology. Where should we begin?
Let's begin by leaving the Earth entirely, the space minerals. Because the IMA list is not restricted to terrestrial geology, it is a cosmic catalog. Look at the entry for armalcolite.
Armalcolite is a brilliant starting point. It was redefined in 1970. The empirical formula is a magnesium iron titanium oxide, and the country of origin officially logged in the IMA master database is simply the Moon.
The Moon, listed as a geographic origin right alongside Spain, Canada, and China.
Think about what that means. Mineralogy isn't just an earth science, it's a cosmic one.
And it is far from an isolated case. The list contains a growing subcategory of minerals explicitly noted as being discovered within meteorites. Akamotoite, a high-pressure magnesium silicate, was approved in 1997 from a meteorite impact in Australia. Alabogdanite, an iron-nickel phosphide, was discovered in a Russian meteorite in 2000.
We also see adrianite, a highly complex calcium aluminum magnesium silicate incorporating chlorine, identified in a Mexican meteorite in 2014, and asimoite, an iron silicate, discovered simultaneously in meteorites recovered in China and Chile in 2018.
The presence of these space minerals introduces the concept of shock-metamorphism. We are cataloging the building blocks of the solar system, analyzing how extreme kinetic impacts and the vacuum of space alter elemental bonding. It makes you hypothesize about the mineralogy of the asteroid belt. If these are the distinct lattice structures surviving the fiery descent through our atmosphere, what incredibly fragile or complex crystallographies exist in zero gravity that we simply haven't cataloged yet?
It forces us to recognize that mineralogy is dictated by the universal laws of physics and chemistry, regardless of planetary origin.
Okay, here's an anomaly from the A section that fundamentally blurs the line between biology and geology. Abelsonite.
Abelsonite is a profound outlier. Approved in 1975 from a discovery in the USA, its formula is nice C31H32N4. It is classified as a nickel porphyrin.
What makes that formula so disruptive to a traditional understanding of mineralogy is the presence of carbon and hydrogen, the C and the H. We're looking at an organic mineral,
Which is incredibly rare.
in a master list utterly dominated by inorganic silicates, sulfides, oxides, and phosphates. Finding a carbon-based organic molecular structure recognized as a distinct mineral species is astonishing.
It speaks to the incredible processes of diagenesis. A porphyrin is an organic compound. We are essentially looking at a biological molecule, most likely derived from the chlorophyll of ancient plant matter or algae that was buried, subjected to millions of years of geological heat and pressure within oil shales, migrated through fracture networks, and naturally crystallized into an inorganic-style mineral framework.
It is the fossilized, crystallized ghost of ancient biology. And it isn't the only one. The list includes acetamide, CH3CONH2, found in Ukraine in 1974, and allantoin C4H6N403, approved in 2020 from the USA. It completely expands the definition of what constitutes a mineral. We aren't just cataloging magma cooling, we're cataloging the extreme, long-term geological transformation of organic life.
The database also serves as an intricate map of global exploration and geochemical variants.
Absolutely. The geographical footprint spans every extreme environment on the planet. Just scrolling through the A section, you find abelomorangerite, approved in 2025 from the Republic of the Congo. You have Antarcticite, a remarkably fragile calcium chloride hydrate discovered in the freezing, hyper-arid environment of Antarctica in 1965. Aphthalite from South Africa in 1925. Afghanite, an incredibly complex sodium-potassium-calcium silicate from Afghanistan in 1967. Alacrenite, an arsenic sulfide from Russia in 1985.
The nomenclature itself is a reflection of this global expansion. Notice how minerals are named after where they are found. You mentioned Jinxuiite from the Jinxuiite region. The list is populated with names like Bianoboid, directly tying the mineral to the massive Ban-Obo rare earth deposit in China, or Alstonite, mapped back to Alston Moor in the United Kingdom.
Alternatively, the nomenclature functions as strict chemical shorthand to describe their elements. Arsenopyrite immediately tells you it's an iron-arsenic-sulfur compound. The massive ammonio grouping, ammonio-alunite, ammonio-borite, ammonio-jarosite, or the argento grouping for silver-based minerals like argentopentylandite and argentopyrite allows geochemists to categorize massive datasets by primary elemental composition at a glance.
The structural variance recorded in the formulas is equally striking. You have elegant minimalist structures like acanthite, which is simply silver and sulfur, Ag2S, or the pure native elements aluminium, approved as a naturally occurring mineral from Russia in 1980, or native antimony, grandfathered in from Sweden in 1748.
And then on the completely opposite end of the spectrum, you encounter formulas that represent almost incomprehensible atomic complexity. Take Abenaki-Itzi, the formula is the Na26, C6, C6018. PO46, CO36, SO2.
That is massive.
That is a massive, incredibly dense structural lattice approved from Canada in 1991. Or Allarite from Italy, which essentially incorporates a massive fraction of the periodic table: sodium, potassium, calcium, silicon, aluminum, oxygen, sulfate, sulfite, carbonate, hydroxide, chlorine, water. Or Amoblite, say, from Canada, approved in 2023, where the empirical formula is so long it requires multiple lines of text just to document the elemental ratios.
This extreme variance from pure native elements to hypercomplex silicates, from extraterrestrial impact fragments to crystallized organic porphyrins, reinforces a critical realization. We are not merely cataloging rocks, we are cataloging the exhaustive capacity of elements to bond, adapt, and stabilize under every conceivable pressure, temperature, and environmental extreme in the universe.
That is precisely the framework we need to apply to this data. Let's pull our focus back from the sheer scale of the 6,200 list and synthesize what we've unpacked today. We initiated this deep dive deep underground in a dark, highly pressurized adit in the Guangxi region of China, examining a microscopic, newly verified lattice of nickel, bismuth, antimony, arsenic, and sulfur, known as Jinxuiite.
We detailed the rigorous, internationally standardized burden of proof, the X-ray diffraction, the holotype preservation required by the international community to transition that physical anomaly into a globally recognized scientific fact, ensuring the integrity of the taxonomic record for future generations.
We analyze the geopolitical and macroeconomic realities driving this science, recognizing that discoveries like Jinxuiite fuel the future of the battery and tech industries. They are vital diagnostic indicators guiding the global mining industry toward the deep vein hydrothermal nickel and cobalt deposits required to power the energy transition. And finally, we zoomed out to navigate the colossal master list itself, the 6,200 ingredients that comprise the solid architecture of our planet and our solar system.
The fundamental takeaway is that the lithosphere is an active, evolving data set.
Exactly. I want you to retain that perspective. The ground beneath your feet isn't static. It is a highly categorized, actively explored puzzle. Catching up on a field like modern mineralogy means realizing that our most fundamental map of the Earth's chemistry is being updated every single month. with new crystallographic data, new elemental configurations, and new geographical origins.
We have been meticulously tracking these configurations for over 3 centuries, and as the continuous updates to the IMA list demonstrate, we have barely scratched the surface.
So I want to leave you with one final forward-looking thought to mull over today. We have successfully cataloged 6,200 distinct minerals. We have found them everywhere, extracting them from centuries-old, hand-dug adits in Europe to fallen meteorites shattered across the deserts of Chile and Australia. But our technological capacity to explore is expanding exponentially. We are currently deploying autonomous probes deeper into the abyssal ocean trenches than ever before. We're designing rovers to sample the regolith of other planets and moons across the solar system. So, as our ability to explore expands, what completely unimaginable, bizarre combinations of elements are sitting out there in the extreme dark right now? What entirely unknown crystal structures, forged under alien pressures and temperatures, are just waiting to be extracted, subjected to X-ray diffraction, and permanently added to the master list? And more importantly, which of those undiscovered high-performance minerals is holding the exact structural properties required to trigger the next global technological revolution? Think about that the next time you look at the ground beneath your feet. Thanks for diving deep with us today.